Well, thank you all for being here. Like I said, such a nice turnout for us today. Welcome. I see some familiar faces. If there's anyone new here, thanks for joining our sustainability coffee chat. This is a monthly, somewhat informal kind of a session where we hear from different experts in all sorts of areas of sustainability and climate, and just have a nice kind of morning discussion here. Hopefully, everyone has their coffee, tea, warm beverage of choice. Just kind of a nice way to start the day. So today we are going to be talking net zero buildings, so the operation of buildings with lower emissions. This is something that is a big part of our current climate action plan on campus and trying to figure out how we operate our buildings um, in a more sustainable way. So we have two lovely speakers with us today. Our very own Richard Graves, who's an associate professor and architect and research director for the Center for Sustainable Building Research. And we also have Robert Ed from Darcy Solutions, which is very involved in the creation of the building that you can see on your screen there, the new collections facility over on the Como area of campus, if you're familiar. And so we are going to kind of get right into it. Um, I think what we'll do, maybe we'll start with you with Richard first, and you can kind of provide some context, and then we'll dig into things with Robert, if that sounds good.
Yeah, that sounds good. Just wondering, just wondering about timing with should I go for like 20 minutes?
That's perfect. Yeah,
Okay.
sounds good. I'll stop
Uh,
sharing.
Let me share my screen. So hopefully everybody can see this. So, yeah, so I can talk about a lot of stuff with net zero. So I'm gonna just kind of try to hit hit the highlights. And Carly, if you can just like give me a warning when I should, you know, at about maybe 9:25 or something. I'll try to keep track of the clock.
Sounds good.
But so net zero buildings. And so personally, I have a lot of experience with net zero buildings. I live in a net zero house, um, that's a reno. And I'll get into there's different types of what net zero means. And so my house is sort of net zero energy, close to net zero cost, and comes and goes year to year, whether it's net zero carbon. Um, but I've also have a long history of I worked on one of for the College of the Atlantic years ago, which was one of the first net zero campus climate action plans. So they had actually did a plan for the campus to be net zero with Rex was their original plan, but I was part of the work of them setting some targets and doing some solar on a farm they owned to be net zero with their own operations, not buying Rex, which I thought was which was good. I worked in a net zero building at the Bullitt Center in Seattle for a couple of years um, where I also did again a bunch of net zero kind of city scale plans for things like University next to Simon Fraser in Burnaby, BC. Here in Minnesota, have worked on things like the Ford site net zero development proposal. That's not going to happen, but at least we knew how to make the Ford site net zero if we wanted to do that. And so what does net zero mean? In general, it means in a year, this is the super basic definition. There are way more complicated definitions that I will get into, but it basically means in a year that your production minus your use is zero. Um, there used to be a federal definition from the Department of Energy of what net zero means that you can't get anymore. But fortunately, I downloaded it before they took it away. And it, means we need highly efficient buildings that are free of emissions on site and these kinds of things, which was starting to be a good federal definition of what net zero meant, which would have meant that we could unlock funding opportunities and other things to kind of support this work around the country. I think I'll quickly go through some of this stuff, but people have sort of talked about what is net zero for a long time. The National Renewable Energy Lab has published a bunch of papers on what is net zero. Um, and it happens at different scales. It starts with efficiency. You could have a net zero building and not care anything about efficiency. You could just have acres and acres of solar panels and just be like, energy efficiency, what? Who cares? But that's not really what we want to be encouraging. We want like first starts with efficiency, get the building as efficient as you can. Then you try to do on-site renewable options as much as possible. NREL created this hierarchy of like solar on the building as one typology, and then you can have site scale solar. But in general, you want kind of solar close to or whatever renewable energy source. Usually net zero buildings are solar powered. Um, but they don't have to be. You want those energy sources sort of close to the building. But then if you exhaust those and you can't do those kinds of things, you can do offsite kinds of things in the portfolio or other parts of the campus, or even that's when you start to get into the rec thing. So there are different types of net zero. There's net zero site energy, net zero source energy. I'll talk about what that means. Then there's net zero energy cost. In other words, like the money that you spend on, you basically have no cost of energy. That's highly variable depending on where you are. And then there's net zero carbon emissions. So here in Minnesota, when we're doing the SB 2030 program, we're doing net zero energy. Um, Typically, site energy is the way we're calculating it, but we can do it either way. Plus carbon emissions, that's our goal. So, skip over some of this stuff, but some of the bigger challenges are there's a boundary problem. Like, what do you count for energy and what do you not count? And where do you count it is a thing. So, that's where the source sites thing comes into play of, we're counting the energy and translating source energy to how we count it on site. And then we're generally trying to count all energy usages. Sometimes you would not count process loads. Sometimes you wouldn't count electric vehicle charging. So that's just something to keep in mind that, what do you count? What do you not count is a thing. Another thing that's important is very rarely, though I have worked on projects where you're net zero and you're not connected to the grid. So you're trying to figure out how to generate energy, store it in batteries, and then bring it back for usage. Um, that's generally not what we're doing. We're typically using your grid connected and you're using the grid as your battery and kind of exporting energy into the grid and then bringing energy back. So anyway, I think I'll skip a lot of this stuff because it gets complicated, but you can, the site source energy is an important thing because depending upon where your building is and how your building is designed, like if you're doing an all electric building connected to the grid with solar on the roof, pretty much site energy is the driver because most of the energy is either within your boundary or counted in the same way. But if you're trying to do a net zero building and you're importing natural gas or different things, then it gets complicated. I'll cut to the chase. Why do you care? So, like all electric zero energy buildings, generally you're using electrical energy, which is um, counted within counting its source energy the same as the solar production. So basically, kilowatt hour or kBTU of energy used is the same as your production. And so it's a really simple calculation. If you get into a building that's not all electric and you have a mix of things where you might have most of your power electric, you have some natural gas, you might be bringing in some district sources of energy. There are these multiplying factors where you calculate up energy used and energy produced to get to net zero. So, um, I think in the interest of time, I'm going to skip through a bunch of stuff, but just to kind of go through a building in detail, which is the bullet center, which explains a lot of the concepts and how this stuff works. You have the bullet center, which 50,000, a little bit more than 50,000 square foot office building in Seattle. Its systems are a ground source, which we'll hear about the Darcy systems, which is a great ground source system. Generally, net zero buildings to be really efficient are using some kind of heat pump based mechanical system. In this case, Bullet used a ground source system that feeds radiant floors. They have natural ventilation, which so it's using some passive ventilation strategies to boost the energy efficiency. And then it has a solar roof generating electricity mixed with some batteries to do some storage on site, um, and using the grid as its battery. So if you look at the building, like a typical code building for this size would have had this amount of energy usage. Then Seattle Energy Code reduced it quite a bit. A LEED Platinum building getting all the energy credits would have been even lower. And you can see that trying to drive to net zero drove the energy budget basically even lower than a LEED Platinum building, about a half of what a LEED Platinum building would have been to get to about a 230,000 kilowatt hour solar budget, that then drives efficiency. This is kind of similar to what we usually see with SB 2030 buildings too. They're somewhere south of the LEED Platinum level for energy usage. And then SB 2030 buildings aren't trying to get to net zero. The jet in high level right now, our target is about half your energy is generated from renewables. So that would be a comparison. So, this is kind of a famous series of slides that, like, here's how big the solar array would have been if you did just a typical building for the bullet center. So it would have covered the whole neighborhood in solar in terms of amount of solar to generate the energy. And then smaller for a code building, smaller, but still doesn't fit on the site for a LEED Platinum building. And then that's the final building. So kind of shows the importance of tying efficiency to production with net zero. And it gets you to um, the uses in the build, getting very aware of the uses in the building. And most of the efficiency strategies start to eliminate most of the heating and cooling loads. So you're just down to plug load kinds of things, powering outlets, powering computers, user-driven loads become the loads that are left after you've driven efficiency as low as you possibly can do it. So you do things like, good daylighting, improved envelopes, heating and cooling again with heat pump systems, thinking about passive systems, um, and then to get to your solar. So it then becomes important, and this is something like after you've done a whole bunch of net zero buildings, this is in the design phase, what you're trying to figure out, which is what is your predicted energy production? Because it's going to go up and down as the year, especially in Minnesota. You're going to have less sun, less daylight, as we know now, as days are getting shorter and shorter and shorter. The sun's at a lower and lower angle, so you start to get kind of November, December, lower production. You get snow events here in Minnesota that cover your solar panels for a couple days till they melt, which takes out production. So generally, this is Seattle, but Minnesota, you have a sim. Actually, we kind of have higher spikes in the summer than Seattle with more production. But you're trying to predict, like you'll do a prediction of what you'll get for production, and then you're trying to see what the actuals are. And then same thing on the energy usage. You're going to predict what your energy usage is, but then your actuals are going to come in. And this goes either way. See, Bullet Center, the actuals consistently came in lower than the predicted. That is not usually the case. Usually you start doing a performance period trying to get to net zero and you find you're a little higher than what you predicted as a more common story. And you try to figure out like what's off track here. Is there a usage? that's off or something else to kind of get that in line. You do have things like a net zero project. I used to teach classes in Seattle, the Birchie School, which is a famous project. The students love the composting toilets. So that project ran it over on its energy usage because kids would come from all over the campus to use the composting toilets that had a pump attached to them, and that drove the energy usage up. So that was, I don't know if, I mean, that was kind of a bad thing because it drove energy usage up, but good on the kids that they thought like composting toilets were fun. So anyway, you just have to man you're managing actuals, which I think is actually the really good thing about doing net zero projects is it really makes you aware of what's going on, what's happening, how do things change over time, and you get really connected to all this stuff to manage it. So there's lots of examples of net zero buildings on campuses, especially living building challenge projects from the Candida building at Georgia Tech. This is actually a project we use in the architecture studios here at the University of Minnesota. We kind of take the Georgia Tech building, which is like these big sweeping roofs in a hot, humid climate, and we move it to Minnesota to be a campus building on the University of Minnesota campus because it's a different climate, different energy usage, and it's kind of a great project for architecture students to think how the design is tied to climate. Um, there are a number of net zero projects. In fact, one of the first net zero projects in the country was a science house at the Science Museum here. And then there's emerging more and more net zero projects. And I'm sure we're going to hear about some of them because a lot of them now are using Darcy systems when they're trying to get to net zero. But Science House, Westwood Hills, so the Science House, it's this project that you've probably seen on St. Paul as you're going by the river and look at the Science Museum. Again, one of the first net zero projects in the country. Wolf Ridge up in northern part, Living Building Challenge project is a net zero project. Westwood Hills, Great Coat Park, um, Lakewood Welcome Center. I think Great Coat Park and Lakewood are still in their performance periods, as far as I know, but others might know if they're actual net zero projects now. Um, and then again, on that list was the Ford site as a district scale net zero project, but won't get there. But we do know how to do net zero at scale if we want to. That's a viable solution in Minnesota. So um, maybe with a couple of minutes left, I'll just throw out a few other things. Generally, when you're trying to figure out net zero at the campus scale, you get into what can we do across all buildings, and it's always comes down to envelope, better mechanical systems, and managing the user-driven loads. Doesn't matter the building type. And then the last couple things, this is all net zero operational energy. One thing you have to, and that creates a boundary of what are we counting? And the other thing to kind of think about is there are other types of energy, other types of carbon emissions kind of in the mix of building a building. And so embodied carbon or the carbon or energy usage to build the building is an energy usage that is let me find that slide. That's pretty significant, actually. So it's something that a net zero building should account for its embodied carbon, and living building challenge projects do that. They have to do an offset to pay for the embodied carbon, but not all programs do that. So I could talk about a gazillion other things. I'll stop there and maybe answer questions after the Darcy presentation. So yeah, that's the vast overview of net zero.
Thanks so much, Richard. I don't know about other folks, and we don't have time to get into it now, but I'm really curious to know more about the house that you live in and how you make that net zero. That
Yeah.
that's sounds like such a great goal, probably for so many folks on the call to someday live in a net zero home. That's so cool. We will kick it right over to Robert, and then we will have some time at the end, and we can dig into all sorts of questions. So, Robert, if you want to take it away.
Yeah, thanks a lot. I really appreciate the opportunity to speak. Let me just share my screen. Um, Try to move this out of the way here. Okay. Okay, so today I just kind of have a lot of generic slides about Darcy just to give people a little background on the company. I spent 7 years working in solar prior to coming to Darcy because I was really excited about decarbonization of the built environment. Frankly, I'm excited about decarbonization of the economy writ large. But buildings are one of the biggest areas of opportunity, and ultimately that's why I wanted to focus on the built environment here. I like to usually start by talking a little bit about geothermal. Geothermal is really important. It's a tiny fraction of all of the HVAC systems in the US and the world. It's less than 1%. And so when you think about the energy efficiency afforded by geothermal, it kind of begs this question of why aren't we doing more geothermal systems? And there's a number of reasons for that. There's a halo effect for existing technologies that are adopted and have a big supply chain behind them in terms of people that know how to install them, OEMs that build equipment that is used in those systems. And then there's just this knowledge gap oftentimes that people don't necessarily understand what geothermal is or why it's a good idea to invest in it because ultimately the capex for geothermal systems is higher than other more packaged equipment coming directly from a factory that might rely on natural gas to provide heating. I like to walk through three types of geothermal. They're shown here on the screen. The far left being the most common type that you'll run into, which is U-bend vertical borings. It's usually a 4-inch diameter boring that's somewhere between 100 and 800 feet. The deeper you go, the more thermal capacity you can derive from it, and that it's dependent on thermal conductivity of the area that you're boring into. The way those systems work is you place a large U-bend pipe into that boring, run a conduit fluid, usually a glycol-based conduit fluid through it, and then pull heating out of the ground during the winter or cooling out of the ground during summer. And you basically just scale up the number of borings based on how much thermal capacity you need for the building itself. The challenge with that is a lot of buildings don't have perfectly balanced loads. So it can be a little challenging to design the system and size the bore field appropriately. And so that's a little daunting if you've never designed one of these systems. But otherwise, it's a really great technology and it should be incorporated a lot more often because it has extremely high energy efficiency, COPs of 4 plus in some instances. And the fact that it's not just showcases some of those other reasons that I highlighted previously that they're not used in design as much as we'd like. Another big reason for that is land constraint. It does take a fair amount of land to build systems like this and then tie them back into the building. The next one I've got there in the middle is pump and reinject, which is essentially a project where you're building a water well, pumping water from the aquifer that you're targeting, and then putting it through a plate and frame heat exchanger within a building, then re-injecting it back into that aquifer in another re-injection well, typically something like 500 feet away. Oftentimes you'll need multiple re-injection wells because of the mounding associated with these projects. And they're also somewhat challenging to engineer because so few people have done that. But they're also really potentially high efficiency systems. And, when coupled with renewable electricity can provide a, uh, a thermal exchange system that eliminates emissions. So also a good idea. I will make a quick side note on pump and dump systems. That would be where you're not actually returning the water to the aquifer. That's, in my esteem, not a very good plan for the simple reason that these aquifers can often take a long time to have the water get to where it is, where you're targeting it. So if you're removing it, it could take tens of thousands of years for water to get to where it was coming from in some instances. And that is a natural resource that we're reliant on. So like just using that water and then basically letting it go into an effluent stream isn't a great idea. Then finally, Darcy system, which is basically a combination of those two. We've got a water well that we construct, and then at the bottom of that, we've got a customized heat exchanger that we place specifically to target an aquifer down the well. And then we couple that with a closed loop back to the building. And that closed loop is providing all of the thermal energy back to during the winter and summer that you need. we're pushing the aquifer water across that heat exchanger, all throughout the year. The submersible pump is usually somewhere between 5 horsepower to 20 horsepower, and that's the open loop element of the system. So we're combining these two things, and because of that, we're able to put a similar amount of thermal capacity that you'd see in something like a pump and reinject system in a very small footprint and not needing reinjection wells. So it's a little bit different than those two other system types, but it combines kind of the best of both worlds. But we're advocates for all these systems, and we've built a pump and reinject system. We just commissioned that about a month ago. We'll likely build traditional systems. We see geothermal as, one of the primary levers by which you can decarbonize buildings in the future. And so we're trying to promote all these technologies, despite the fact that today the most common one that we're building is that last one. The technology actually came from the University of Minnesota. Our chief scientific officer, Jimmy Randolph, worked with Scott Alexander, who's a researcher at the University of Minnesota, and they started kicking around this technology and ideas. So it's that was a long time ago. That was in the early 2010s. We incorporated in 2018. We really didn't start seeing market traction until post-COVID. So kind of a lot of information, but I'm an alum of the U, and I'm very proud of the fact that we came from the school, and hopefully we can continue to innovate and come up with new solutions that we can use to decarbonize buildings as well. So maybe a little bit more of a deep dive on Darcy's technology. Today, we can produce upwards of 300 tons of cooling from one 12-inch water well. That's more than enough for many, many building sizes. And you can do that in the footprint of about 2 feet by 2 feet for a water well. So you could easily put a well 5 feet outside your building and be able to provide the heating and cooling you'd need over the course of the year without having the requirement for all that land mass. And that's a really big opportunity for a lot of design engineers that maybe weren't thinking about doing geothermal before, but have customers that are also interested in sustainable operations of their building. The other element to touch on is the fact that the investment tax credit is available for geothermal, and that will be available through 2034. So unlike solar and wind, which were eliminated in the OBBB, I like to call it Big Bill for short, the geothermal technology is still going to be in place for the incentive tax credit, and that means you can get up to 30% for prevailing wages and apprenticeships, 10% for domestic content, and if you're in an energy community, 10% more. The other powerful element of this is that any equipment on the building side of the system, if it's energized by geothermal, it also qualifies. So it really lowers that CapEx problem that a lot of budgets were challenged by in terms of geothermal historically. So a couple other things that are of interest. We already talked about small footprints and the total cost of ownership element of it, at least some parts of it. Unbalanced loads, when you're using the aquifer for doing this type of a system design, you get a natural movement of the water in that aquifer over the course of time, which provides a recharge over the seasons. It doesn't move very quickly. It's not like a river underground. It's moving maybe a couple feet a day, depending on the aquifer. But ultimately, that means that the design constraint associated with having a perfectly balanced load is eliminated. And so we can adapt to a lot of other building site applications. Interestingly, there are some aquifers in Europe that are not moving. They're kind of a standstill aquifer, whereas everything in the United States does move. Comparatively, this is what the systems look like when you look at conductive thermal transfer versus advective-based thermal transfer, which we're doing. Essentially, we're just harnessing the entirety of the thermal mass associated with the aquifer by using water as a conduit fluid as opposed to the soil directly around the boring. So when you consider how much space you'd need for a traditional system, we tend to call it traditional geothermal when we're talking about 4-inch diameter borings. You're going to need approximately 25,000 square feet or a little bit more than that for one well. So it really eliminates the possibility to use this in a dense urban environment, traditional that is. Whereas if you were to put 4 wells around a building in an urban environment, it's certainly going to have a little bit of challenge as far as where you're going to place everything, how you're going to pipe it into the building, but it's within reason as far as how much land mass you actually have. Another really fun thing to think about is where we're going as a company. We've been expanding the thermal capacity of these systems pretty consistently over the last 3 years, about 15% per year on both heating and cooling. Today, we're on our 8th version of the heat exchanger that came out of the university. And then next year, I think we're going to be on to our 9th version. We're also innovating in a lot of other ways in terms of the balance of systems, the equipment used to finalize the completion, things that make construction easier, things that lower the total costs, and just basically improving the value chain associated with all the elements of how we build these systems and commission them. When you first introduce a technology like this, there's a lot of knowledge curves to get down, not only in terms of what the design should be and how to optimize them for specific building applications, but also in training the workforce to be able to install it efficiently and take advantage of it. On the inside of the building, this is the most common layout we're going to see. We've got a controller box that can house up to 16 wells. The largest system we have today is 12 wells, and the number of wells tends to keep going up in terms of our average size. We have variable frequency drives that control the pumps down well, and then we usually home run each well into the mechanical room where it's manifolded and then connected to a larger closed loop for the building. We do tend to have a intermediary heat exchanger between the building side loop and the ground source loop. And we can also use the system in lots of different other configurations. So we have VRF systems, we have chilled beam systems, distributed heat pumps, and there's a number of other ways you can use this. I mean, essentially, if you can take advantage of the thermal capacity coming from the aquifer on the applied side, you're going to be able to design a system that'll work well. Maybe just a few images. Here's the OCF project, which, by the way, I was really impressed with when I walked through it. I had no idea what the project was for. When I heard offsite collections facility, I just didn't really understand what that meant until I walked through it. And it's an absolutely gorgeous building. And it's a really cool story to think about what that building's purpose is. And ultimately, that's where I've landed as somebody that's trying to explain the benefit of these systems. When you talk about buildings, you need to talk about why the building exists and then why you're trying to, have a sustainable operation for it, as opposed to the mechanical equipment that you're using. I think some engineers are probably very interested in mechanical equipment, and I think the broader public writ large is more interested in big themes about how we build and operate these buildings as opposed to the specific uses of heat pumps and geothermal equipment and all these things. So I tend to try to figure out what's the story of the project itself. And this is a really beautiful building and, again, a really fun story to talk about. Down in Rochester, the city hall is using our system, and they're actually expanding, trying to build out a thermal energy network along a corridor down in the city, which we've got another 5-well system going in right now. There are a lot of Olmsted County projects happening in general, very progressive as far as sustainable buildings go down there. This is an example of wells very close to a school down in Winona. I think this one is actually Washington Kosciuszko, but we also had Jefferson Elementary that was just a few miles down the road from that as well. A little bit different of a project. It's a retrofit, and trying to understand why the schools are so interested in this and how it comes together is also really important if you want to deploy the technology writ large. So there's a number of other projects that we're starting to build out case studies for today. That's one of the challenges for deployment in this industry, is that the project development cycle is elongated. It takes 2 to 4 years for a project to go from start to finish. And after you've done so, then you can actually start to capture these stories, explain it to the market and the viability of these technologies. But it's been a slow burn. I've been here at the company about 3 years, and finally getting these case studies out and into the public eye is the goal today, so that people can understand the technology a little bit better and then consider if it's a good fit for their use case. Beyond that, I've got a few slides on geologic complexity. I realize we're running short on time, so I'm just going to go really quickly. Part of what Darcy does, I'd say what separates us from most entities, is that we're mostly comprised of geologists that can assess a site and if our technology is going to be a good fit. This particular slide is a bifurcation of the MSP area, and you can see the Mississippi River here. There's a number of aquifers that you could target as you look at this particular area. But the deeper you go, the more capital intensive the build will be. So you want to target a shallower depth if you can. And you also need productivity. So the Prairie du Chien is a really good opportunity for us to target here in Minnesota. It's very productive. Deeper than that might not be as interesting because of the economics. Above that wouldn't necessarily be as productive. And so trying to understand specifically where the aquifers are on your site is what Darcy does. If you scale back from that view, you start to realize the Prairie du Chien actually erodes away at different parts throughout the metro. So having a team that can qualify and assess which aquifers are going to work for your project is what we do. If you change to a bird's eye view, looking down at the metro, this is just the MSP area, you start to see all of this marbling of different bedrocks that you run into first. Because this happens because of the glacial period where it's stripping away different aquifers at different areas. And so you have to be able to look at the geologic cartography and try to understand what you're likely to run into, and then build a plan to build the project accordingly, usually via test well. We're blessed with really good resources here. This call out here is some of the red dots that we've looked at projects and the marbling associated with the different aquifers that you could potentially be using or have to think about how to construct a well around. So all this is just to share that this is actually much more complicated than drilling a well and then trying to figure out how to build the system. You have to figure out viability, and then you have to match the viability and productivity of the aquifer to the actual building load that is required to make sure that it works. Last couple slides here is just to point out that you can use superficial aquifers as well as bedrock aquifers to design these systems, and that's part of what we offer. But it's very complicated. I pull these maps up just to show the amount of differentiation that happens at a larger scale. It's very similar at a micro scale. You'll have projects that will be viable in one part of the site, and then 500 feet away, it will be a significant deviation. That doesn't always happen, but it can. And so you have to be aware of that in order to make sure you design the system properly. Okay, I'm going to stop there because that was a lot of info. Happy to answer any questions. Thanks again for allowing me to speak. It's cool to be a part of this group.
Robert, of course, thank you so much. This is all so fascinating. So with our last 15 or so minutes, we just have time for open discussion. So no need to raise your hand, just go ahead and unmute, and we can ask our speakers some questions.
So, Richard, are there any examples of net zero building retrofits
Mm.
in Minnesota?
Ooh, retrofit. Not that I can think, but around the country, there's tons of them. And with that, so, and the other thing I would just mention about the Ford site, we were planning a district scale aquifer thermal exchange system there, which is the cool thing about Darcy is now you can do that pay as you go, building by building. So the world's totally changed from 15 years ago when we planned that, which is a real um, kind of business model advantage. You don't need a big capital investor. So yes, not that I can think of. I'll check the list, Steve, and see if I can find a Reno. But it's kind of markets we typically do the new stuff first because new stuff's easy. But if you look in the Northwest and all around the country, there's tons of retro examples. Because they're not as hard as we think they are. We kind of think, oh man, like how am I going to go after that new building? But especially older buildings that were done thinking of passive systems in mind, passive ventilation, good daylighting, this kind of stuff. There's usually good bones there that you can kind of leverage efficiency and things around and do the other stuff you need to do. So
Richard, I have a couple questions on the slides you had.
yeah.
You had a slide that was a graph that showed solar production coming and
Mm.
going, and knowing that Robert with Darcy was here, do you foresee doing a similar graph that would be considering geothermal and that it's consistent or?
Mm.
Because that slide really only spoke to solar as a renewable energy. Well, I
Yeah,
mean, it spoke to renewable energy, but
yeah, but well, and what Robert's talking about is really a ground source system that's an
right,
efficiency system, not a so you are,
true.
but there's probably an efficiency of the exchange that I'm now in Robert's universe of expertise. That,
Or if
that
there is or isn't.
yeah, I don't know the answer to that. He would know that. Yeah.
Yeah, I get the way I'd characterize this is the aquifer temperatures themselves are relatively stable. So here in Minnesota, where we're sitting, I'm down in Bloomington right now, but it's typically about 52 degrees Fahrenheit. Usually an aquifer temperature is going to be about the mean average of the air throughout the year. And so you can think of it as this constant source of thermal capacity that you can draw from, but ultimately the building load requirement is going to dictate how much energy you're going to want to be pulling from that, right? So it's if it's a particularly cold January, you're going to be wanting to provide more thermal capacity during that time frame to provide that. You might have an increase in the kilowatt draw of the pumps, and that accordingly would require more electricity, right? So
Hmm.
it's kind of really just weather dependent, and so you'd almost need like a P50 and a P90 of what you'd expect in terms of overall the weather itself and how it relates to how much thermal capacity you'd require given the building. I've never really seen that personally. I came from the solar world where P50s, P90s were for every single project you do, but I'm certain it's within like the realm of what we could do in terms of design or thinking of how you'd think about it. Generally, we just kind of we build these systems for design days and then, operate after that.
Yeah. And one thing to think about, Dana, and this is from my house, with solar production, I mean, usually we have a scarcity mindset with this stuff, is like we have to use less and all that. And as soon as you have solar and batteries on your house and you're doing stuff, you realize, because I had a year where I was trying to run on battery as much as I was trying to island my house. You can't do that in Minnesota physically. You have to like electronically island your house to follow the law. Just keep that in mind.
Right,
Um,
right, right.
but you can electronically island. But what you find is so I would run on battery all night long, and then the solar would kick on, especially in the summer day, and you recharge your batteries really quickly, and you're then dumping power into the grid.
Hmm.
And so what you start to think about is are there other ways that I could store the energy rather than just dumping it into the grid? And so things you can do is like pre-cool your house down because I'm cooling on solar, drop it down. And at first you think, like those of us who are so used to efficiency things, you think, what are you talking about? Like, why would I drop my house to like 60 something in the summer? You're so wasteful, blah, blah, blah. But it's all that power is from the solar. So drop it. And then later you just t turn everything off and it slowly comes up. And I think like thinking about all these things interconnected, especially with Darcy systems, and how could you use some of these things to rebalance and do other things to do thermal storage. It doesn't all have to be electric, even at building scale, is probably the future of this stuff. So sorry that was too much information, but it's an interesting thing to think about.
I have a question for Robert as well. So, the Darcy systems, what you commented on the aquifers and having to identify the location of it to make sure that it's viable for a project location. What are other factors that would make Darcy not viable in a location or that you see?
Um, honestly, there's not a whole lot else that would say we can't build in a given location. What we tend to do when we're looking at projects, if in a new location, we have to make sure that we can have the project permitted. Here in Minnesota, that's not any issue whatsoever. But in a new state, oftentimes we work with a different AHJ to try to understand who actually has authority. And sometimes that can be the DNR, sometimes that can be the Department of Health, and it can be administered at different levels of the state, city, municipality. Outside of that, it's having the right partners to actually go build the system. I'm very specific when I say the placement of the equipment itself is really important. So you might have an aquifer, but actually like how you place the equipment within that aquifer is very critical. So the test wells will often tell us exactly how to construct a well and to place that equipment as well. But it really just is there availability of water, and are there any negative elements of that water? We haven't ran into a place where there's been like water chemistry that's been really problematic and we couldn't use the system, or we'd anticipate some sort of different equipment materials requirements, but nothing comes to mind, honestly.
Okay, great. Thanks.
Robert, your slides mentioned thermal energy networks. Um, is Darcy working on connecting wells to existing thermal energy networks? I'm thinking of the university's district heating systems and the extent to which Darcy Wells might help offset the need for imported fuel to fire those systems.
Thanks, Steve. It's a good question. Yes, absolutely. We're very interested in the space, working with some projects to consider how we'd be able to couple in with existing projects that want to expand. Rochester's a good example of that. And then beyond that, we're seeing a lot of, I'd say, smaller scale developments like neighborhoods scale. Obviously, you all are probably familiar with the Eversource pilots going on, and then we're starting to see some more legislation. Illinois just launched or just passed legislation that's going to commission $20 million, I think, for tens. And so I see this as a really big part of the future, but it's also a future that is somewhat dominated by it being public good, which tends to slow things down a little bit if you're familiar with utility business models and how they do deployment. It'll probably be a slow train, but absolutely, we think that we're going to be a part of that. And I personally get very excited about it because I think that's the only way that this technology scales to the level that we really want it to, which is nationwide plus. And it's not just Darcy technology; it's geothermal. How do we electrify buildings? Then how do we make sure the grid is like overbuilt with solar, wind, and batteries or other non-emissions resources, such that we're actually bending the curve like we want?
Thanks.
Robert, maybe you said this and I missed it, but is Darcy, I mean, CapEx aside, it sounds like Darcy is basically feasible for like a typical individual residential lot, like a Minneapolis lot. Technically feasible. It's just kind of
Yeah, technically it is. CapEx wise, the unit economics aren't great. It's just too hard to scale it down to that level and make it work. Um, it's funny, I didn't know anything about water wells. I remember my dad telling me about getting a water well out. I grew up in Alexandria on the west side of Lake Ida, and so that was the most I knew about it. But like drilling a water well is not cheap. The amount of money that has to go into it as far as casing and grouting and all the equipment to connect it make it kind of challenging. And it can produce so much energy that it works really well when you need more than one well or when you need just enough for one well. But for a singular house, thermal energy networks are going to be what we want eventually.
yeah. And it sounds like even as like let's say equipment gets cheaper or more available, there's still all that site work. So there's kind of a built-in floor to the CapEx.
That's kind of how we approach it with the market. We get a lot of residential folks reaching out and just saying, "Hey, would you build on my site?" And we try to be polite about saying this. Probably we inherently kind of know the unit economics aren't going to work for most people. Now that said, there are some people that probably could afford it, but generally speaking, 99% of the market wouldn't want to build a system that costs that much more than what you're already getting from the more traditional systems. So I think the impetus really is this is one of those situations where government and the utilities as a whole have to step in and think through how do we thoughtfully design these systems for the outcomes we want, which I do think is happening in Minnesota and many other states if you look at things like the NGIA. But for a lot of folks, it's not happening quite as fast. I'm one of those people. I really want to accelerate deployment. That said, it's a public forum and we have to be respectful of that.
Thank you. Thanks, everybody.
Well, I have a question if no one else does. Um, I'm wondering just what do we think the future of net zero buildings on campus looks like? I know we're moving in the right direction. We've got some great examples of buildings that are really operating in a more efficient way that aren't technically net zero. I'm thinking of buildings on campus where we've got some great adaptive reuse going on. I know we've got some energy efficiency folks on the call. What do we think the future looks like for net zero buildings on campus?
Not sure if anyone else is going to pipe up on that one. As we all know, I think we all know, it can get down to budget. And in capital projects, since the climate action plan came out 2 years ago, we have on 5 pre-designs on projects evaluated what it would take for those projects to be net zero. Only one of those projects has moved into design. It is not pursuing net zero. It's a kind of an unusual university project anyway. But I can't say right now if any of the rest of those would be expecting or assuming net zero when they move forward budget.
Yeah, well,
I mean, and for that matter, I'm sorry.
oh no, no,
We are at SB 2030 90% reduction for energy. So I'm not saying that's good enough or equal, because it's not. There's still that extra 10%. And I will say we've evaluated that it is the engineers that we've been consulting with have been reducing the energy demand in our buildings, which has been amazing. And we're getting there. But at this point, it's all about the renewable energy for that gap, which can then, in a way, be up to us more broadly at the university. How to treat that gap.
yeah. And just building on that, I think because of existing assets like across the whole university, like doing net zero more at the campus scale examples that I showed, like the Ford site or the University is a kind of going to be the most cost effective, energy effective, if also factoring in carbon emissions of building stuff. We want to figure out how to like build the fewest things to get to the operational net zero. So it's like a base load, which is kind of in the climate action plan in the thinking. It's just like taking it to the next level. But I would say if I ran the universe, which I don't, but a really cool demonstration building like a Candida that is like, here it is right in the middle of everyone's awareness, where you've got a building that's net zero and you can show how all that works like in a one thing would be a valuable kind of education tool because it's hard to district scale things are really cool and fun and efficient, but they start to stretch off to be a little bit abstract. And it would be good to have even a science house scaled thing where it's like, here's a thing and it's generating this and we're using it like this. And here is just building our way of thinking like that. Because I think for our students, we like in the architecture program, every architect that leaves here now designs a net zero project. They have to model it, they have to think about that, they have to know how it's done. And it just sort of builds a skill set that is then transferable to a lot of things, even though probably a one by one by one net zero building approach isn't the solution to our future. So
Richard, I know that those of us in the Office of Sustainability would love to see something like that we could really showcase and educate our community on. So maybe that's something for the future. We'll remain hopeful.
yeah.
Any last minute questions for our panelists? Cool. And Dana, thank you for chipping in as well. I was somewhat directing that question in your direction. So
I suspected.
Awesome. Well, great turnout today. Thank you all for being here. We are not looking at having one of these in December. We want everyone to enjoy their holidays, go off on vacation. But we will see you in 2026. So Thank you all. The recording will be available online here in the next few weeks.
Actually, is there any chance the presentations would be available?
I think
Yeah.
we can.
Yeah, I can
Absolutely.
share mine's like 3 times more slides than I showed.
Right,
So
but there's some pretty,
yeah,
I mean,
yeah,
pretty valuable stuff there and information.
yeah.
Both of them actually, Robert, yours too.
Yeah, I'll send it to you, both you guys right now, Carly and Dana. And then Carly, you can share it broadly.
Yeah, that sounds great.
Thanks,
All right.
Robert. Nice to see you too, by the way.
It's good to see you. Thanks, everybody. Bye-bye.
Thanks.
Bye.